Hello, welcome back to es346 Basic Thermodynamics. This is module 4.1, boundary work, and the textbook sections are section 4.1. Alright, so let's return to our course outline, and we're now moving into the second part of the class where we're going to look a lot deeper at the first law of thermodynamics. We're going to do this for both chapters 4 and 5. We're going to be looking at closed systems in chapter 4. That's what we'll be doing today. When we move into chapter 5 in the next module, we'll look at open and unsteady systems. So here are the two learning objectives that we have for this module. At the end of this module, you'll be able to calculate moving boundary work, and you'll be able to describe a polytropic process. So I want to give kind of an overview of different types of systems, and this was covered back in module 1. And when we have a system where we can define as by either a control volume or maybe some controlled mass, we could have a closed system and an open system. And what we meant by there was whether mass was entering or leaving the system. So if I have mass and it goes into the system and or it leaves the system, then I have an open system. If I don't have any mass entering or leaving, then it's a closed system. Now there's another distinction I can make, and that is whether it is a steady or an unsteady system. If it's a steady system, that means if I look at it at some time t1, and then I look at it again at some later time t2, I guess I should use lowercase t's for time, if nothing has changed, the system looks exactly the same, then it would be a steady system. Now if at a later time something had changed in the system, I would call that an unsteady system. Closed systems and open systems can be either steady or unsteady. Now think about a steady system that is closed. So I have no mass entering or leaving, and it's not changing. It's just sitting there. It's just got a set of properties. And we've actually looked at that already. So we could say we've looked at that in chapter 3, in the previous module. What we're doing now is we're going to be looking at closed systems that are unsteady, and that's going to be chapter 4. Then when we go ahead and move on to chapter 5, we will have open systems, and we'll look at both steady systems and unsteady systems in chapter 5. All right, I want to return to this concept of boundary work. We've discussed this a few times, but it's a pretty important concept, particularly for closed systems. So again, imagine I have this piston cylinder. So I have a tight-fitting piston that can go ahead and move within the system in and out. And if I exert a force across here, that force required to compress the system could change as a function of x as I move through here. And we know that pressure is force per area. And the amount of work that I do, boundary work, is the integral of F times dx in this direction. Now if I go ahead and change force is equal to pressure times area, I can go ahead and convert this equation into the integral of P dV, where the area is the cross-sectional area of that piston. Now in order to do this integral, P dV, I need to know what the pressure is as a function of volume. If it changes as the volume changes, I need to put that in before I can go ahead and do that integral. And that's going to be the key of everything that we're looking at in today's module, is determining what is that PV relationship. All right, so the first case we're going to look at is isothermal compression. So again, I've got a piston cylinder tightly fitting. I'm going to go ahead and compress the system here, but what I'm going to say is that T remains constant within this piston cylinder. And so, not surprisingly, I'm putting energy in. That means that there's going to have to be some heat flux that leaves the system as I compress it to go ahead and keep that temperature constant. So I want to go ahead and calculate my boundary work, which is the integral of P dV. Now, although the temperature remains constant, the pressure can change, and I need some sort of description of what that is. So I'm going to make a further assumption, which is that it's an ideal gas, which means I can say P is equal to mRT over V. And T is a constant, so I'm going to call it T naught. So if I put that in for the pressure, and now have the integral of mRT naught over V dV, and I can bring out that out of the integral because it's constant. So now it's mRT naught, the integral of dV over V. And that I can go ahead and integrate. So now that's going to be m r T naught, the natural log of V2 over V1. And furthermore, MRT naught is a constant. I could do another replacement and just go back and replace P1 V1, ln of V2 over V1. Or I could have went ahead and used the end states as well. P2 V2 natural log of V2 over V1. Because at every state, PV is a constant. That's what happens during an isothermal process. Okay, let's go ahead and look at a polytropic process. And so again, I'm going to have a compression that's occurring, but now T is not going to be a constant. So there's going to be some heat transfer, but probably less than I had that was required to go ahead and keep that constant. If I was to go ahead and plot pressure as a function of volume, if I think back to the isothermal case where T is a constant, it might follow that line right there. Now, if I had something that was not constant, so the temperature went up, but T is not a constant there. So if the temperature goes up somewhat, at each volume it's going to have a slightly higher pressure. So I might follow that dashed line there. It means I have some heat transfer. When I have some heat transfer, that's called a polytropic process, in contrast to an isothermal process. And so I'd like to know what that line is, because that right there is my P as a function of V relationship that I need in order to go ahead and put into my equation for the boundary work. We call the boundary work is the integral of P dV, and I'm trying to put something in for P. Now, if there's some heat transfer and I don't know how much it is, unfortunately at this point we just have to throw up our hands and go and measure what that is. So make a series of measurements at different volumes and different pressures and determine what that line looks like. And by convention, it found that if I was to go ahead and define an equation where PV to the n is equal to a constant, I can go ahead and fit that line pretty well. This is a purely empirical fit, and if I do that, I'm going to determine some value of n. That value of n is called the polytropic constant. I could rearrange this equation and say P is equal to the constant over V to the n. So again, this is a P as a function of V relationship. And so what's that value of n? Turns out n doesn't vary all that much. The lowest value n can be is 1. In fact, if n was equal to 1, you look over here, I would have P V to the 1 is equal to a constant. And that constant could be, for example, MRT naught, which is the isothermal case. So the isothermal case is n is equal to 1. And if n is something larger, I have a polytropic case. You might wonder, what's the maximum value of n? And it kind of fluctuates, but they're not much more than about 1.5. So it's actually a very, very small range of polytropic exponents that I can have. But since it appears in the exponent, it actually has a pretty dramatic effect. Let's go ahead and do that integral. So we wanted to go ahead and do the integral for the boundary work, the integral of P dV, and I'm going to go ahead and put in that polytropic expression that I had before, which is that, I'll write it here, P V to the n is a constant C, or P is equal to a constant over V to the n, or C V to the minus n. So I'm going to go ahead and put that in here. So what I have now is I have C V to the minus n dV. And we'll go ahead and do that integral. So I'm going to go ahead and pull the constant out and integrating V to the minus n. So 1 over minus n plus 1 to the V minus n plus 1. All right? And I can go ahead and reorganize that as well. So I've got a constant. I'll move my negative. I'll have over here 1 over minus n plus 1. V to the minus n times V. Because V to the minus n plus 1 is V to the minus n times V to the 1. This right there, V to the minus n times C, we realize is just equal to the pressure. So now I've got 1 over minus n plus 1 P times V. Evaluate that from point 1 to point 2. So if I end up doing that, this is going to be my final expression for the boundary work. P2 V2 minus P1 V1 over minus n plus 1. Furthermore, if I have an ideal gas, which I haven't assumed yet, but if I go ahead and assume I have an ideal gas, PV is equal to MRT. So that actually equals into MRT2 minus T1 over minus N plus 1. So this over here is only true for an ideal gas. This is true for any gas, and they're both true for a polytropic process. All right, let's go ahead and do an example here. So we have a piston cylinder device, and it is compressed. So I'll draw my piston cylinder here, and it's compressed, and I have an initial pressure, P1 of 100 kilopascals, and the initial volume is 2 cubic meters, and it's compressed to a final volume of 0.5 cubic meters, and I know what the value of N is 1.2. And I want to know how much work was done. So I know that I've got a polytropic process. N is equal to 1.2. My boundary work equation for that is P2 V2 minus P1 V1 over minus N plus 1. I've got both my initial pressure and volume. I have my final volume, but I don't have my final pressure. And I can get that, though, from that polytropic relationship, because I have P1 V1 to the 1.2 is a constant, which is also equal to P2 V2 to the 1.2. And there's one equation to go ahead and solve for what P2 is. So P2 is going to be equal to P1 V1 over V2 to the 1.2. If I go ahead and plug those numbers in for the pressure, I realize the pressure is 528 kilopascals. So now I can come back into my boundary work and put that in here. 528, and my final pressure, final volume 0.5 minus 100 times my initial volume, which is 2, all over minus 1.2 minus 1, and I can find out my total boundary work is 320 kilojoules. All right, now I want to look at another type of work here, where now I've got a piston cylinder device and it's expanding, but it's expanding against a spring. So recall again, what we're trying to get boundary work, integral of PdV, and we want some expression for what the pressure is as a function of volume. And so as this pushes against the spring, if we assume this is a linear spring, meaning that it's moving with small deflections in the spring, the force that's exerted is some spring constant times x. So I could go ahead and plot what F is as a function of x, and it might look like that. Now recall, the force is the pressure times the area, and x is that distance I'm compressing, so that right there is actually the volume over the area. So F equals kx is like pressure times area is equal to k times volume over area. We bring the area over, and our pressure is equal to k over a squared times v, and I now again have a PV relationship that I could go ahead and plug up into that equation to do that integral. Now, before I do that, though, I want to point out something. Let's just think what this looks like on a PV diagram. So I have some initial state 1, I'll put it right there, and the pressure as it increases, as the volume increases, and it does that linearly to some final point up here, point 2. And what I want is the integral of PdV. And recall from calculus, that's just the area underneath that curve right there. And what this is this looks like it's kind of like a trapezoid on its side. So I actually know what that area is just from the trapezoid rule. But I could say the boundary work is 1/2 P1 plus P2 V2 minus V1. So there's point 1 and point 2. So right there is my boundary work equation. It's the same thing I'd get if I was to go ahead and plug that pressure in. It's just a little bit more calculus and algebra in order to do it. All right, let's go ahead and do an example here. Another one. So now we have a 2 cubic meter piston cylinder. Volume doubles against a spring. So I'll throw my spring in here. And the pressure changes from 100 to 200 kilopascal. I don't know what the boundary work is. Well, we just saw what that equation is. It's 1/2 P1 plus P2 V2 minus V1. This is going to be pretty straightforward because I have all of those numbers there. So 1/2. The initial pressure is 100. Final pressure is 250. And my volume changes. It goes from, doubles from 2 to 4. So I'm going to end up having 4 minus 2. Let's go ahead and put our numbers in there, and that comes out 350 kilojoules. So there's what my boundary is.